General relativity, step by step. I'm going to return to the Riemann Christoffel tensor of screencast 58, and I've just copied down the equation there. I've just changed the notation a little bit. I'm using Greek indices rather than Latin, and now I'm going to use the comma goes to semicolon rule. It's beautiful, beautiful system here. What I'm going to do is take this complicated mess of second derivatives and Christoffel symbols and all this lot, and then what I'm going to do is to transform. I'm going to consider this in a local inertial frame which has got a nice symmetric and constant metric tensor, and of course that's my G alpha beta, and that doesn't change, so the derivatives are 0. The second derivatives might not be 0, but the first derivatives are 0, and that makes my life a lot easier. So I've written down the definition of the Riemann Christoffel tensor with 1 superscript and 3 subscripts, and I've put in red. Red symbolises the fact that I am contracting over that index. So it's a repeated index, and therefore I'm summing over it. Okay, so well, let's think about the Christoffel symbol alpha, beta, gamma, and that equals a half. And I'm going back to screencast. I can't even remember what number it was now. Whatever number it was, a half G. Now let's see if I can get this right. This alpha here, which I'm going to write in red. No, I'm not red. I'm going to write it in green. That alpha is that alpha there, and I'm going to sum over a red index. I think red symbolizing. I think red symbolizing a summed index is quite a good notation. So I've got alpha, beta, gamma. Let's try a delta. Okay, so I'm going to sum over deltas, and then I'm going to say di G blah blah by di X blah plus di G. See how I'm writing the skeleton in, minus di G blah blah by di X blah. And I'll write the blahs in now. So the first thing to consider is, what does my delta sum with? What does my red delta sum with? Well, it's going to sum with the first index and the second index and the bottom index. And you can see how there's a symmetry between, oops, that's red. There's a symmetry between the first two ones, which is broken in the bottom one because I'm summing over the differential variable there. Where does everything else go? What have I got? I've got a beta and a gamma to sit somewhere. So it's got to go beta and gamma, beta down there, gamma in the first one, and beta and gamma there. Equals what? Well, in a local inertial frame, in which I've got my my metric tensor being this nice diagonal form here. So that's me, and I'm sitting in space, and I'm going to fall into a black hole, and I'm terribly worried. So I build an elevator on myself and say, right, there's my fundamental tensor, there's my metric tensor, deal with it. Well, that's equal to 0 for me. Well, of course it's equal to 0, because that's 0, because the metric tensor is just a matrix of 1s and -1s and zeros. All these terms are 0 in a local inertial frame. So in a local inertial frame, the Christoffel symbols are equal to 0. That's nice, isn't it? Now, well, we know that that's the case, because a local inertial frame is flat, and in a flat space, I can set up Cartesian coordinates, and in Cartesian coordinates, or I keep on saying Cartesian, what I really mean is orthogonal coordinates. It's Minkowski space, I guess. But I can set up flat coordinates or uniform coordinates, and look how much easier it makes my Riemann Christoffel, because these terms here just disappear. This product term disappears. Well, that's nice, so I'm going to write it out. In a local inertial frame, which is my elevator frame, there I am, in my elevator, my Riemann Christoffel tensor looks like this. Beta, mu, no, I may as well keep consistency with what I've written. Mu nu equals di lambda beta nu by di x mu minus di beta mu by di x nu. All I'm doing is copying from here. Well, that's nice. Which is not necessarily equal to 0, even in a local inertial frame. Even though these terms are 0, their derivatives aren't. I mean, I can have some curve, like a parabola. The differential of that parabola is 0 at the origin, but it's got a second derivative, so y dash equals 0, but y dash dash is non-zero. Okay, so let's evaluate it. Let's just evaluate it. Actually, it's easier to evaluate. It's easier to evaluate the Riemann tensor with all four indices down, alpha, beta, and it's conventional to write it like that. Different people, I mean, sometimes you see it A, B, C, D, but I quite like the distinction that Greek indices are summed 0, 1, 2, 3, and Latin, Roman indices are 1, 2, 3. So this is just the space components, and that's just a nice convention. So what I'm actually going to do is to evaluate, I won't do it on this screencast because it's already gone on too long. I'm going to evaluate R alpha beta mu nu, which equals this thing with an index lowered. So it's fundamental tensor alpha, let's call it pi, R pi, and then beta mu nu. I'm going to evaluate this thing here using that equation, but I'm going to do it on the next screencast. I'm going to stop there. Stop.